Welcome back, ladies and gentlemen, to the next part in our Introduction to Mathematics course. This video is on equivalence relations. And the content will be that first I will introduce equivalence relations and we will study some examples. In the second part, we will study so-called partitions, which will give us a better set theoretic understanding of equivalence relations. And in the third part, we will learn about modular arithmetic. And this is an example of how equivalence relations can be used in mathematics to construct new algebraic structures. And finally, in section 4, we will see in which sense maps between sets can be compatible with an equivalence relation. We begin by introducing equivalence relations. So in the previous chapter of this course, we learned about relations, and the most important class of relations are equivalence relations. And as their name suggests, these relations express that certain elements of a set are equivalent with respect to some property, which for now I call P. So when we study a problem on the set X, in which this property P is the only criterion that matters, then we can regard the equivalent elements as identical in the context to this problem. So whatever makes two elements that are equivalent with respect to property P different is not relevant for the problem at hand. So this allows us to think of equivalence relations as generalizations of equality. So that's an important point of view to have in mind when studying equivalence relations. And later in this video we will learn about a very important construction to turn an equivalence relation into an actual equality. Let's get to the definition. So if X is a set and we have a relation rho given, which as you may recall is a subset of the Cartesian product of X with itself, then we say that this relation is an equivalence relation if it is reflexive, symmetric, and transitive. And just as a quick reminder, the relation being reflexive means that any element of the set X is related to itself. The relation is symmetric, means that an element X being related to an element Y is the same as saying that the element Y is related to the element X. And the relation being transitive means that if X is related to Y and Y is related to Z, then X is also related to Z. To denote equivalence relations, we usually use this tilde symbol, and then we write just X tilde Y to express that X and Y are equivalent. Usually I will just read this as X equivalent to Y. Other symbols you'll often find for equivalence relations are these variations of the equality sign. So here we have these 3 bars, or here we have the 2 bars of the equality sign together with a tilde, so you will often see these symbols too. And since we view equivalence relations as generalized equalities, it would be reasonable to expect that the actual equality relation is itself an equivalence relation, and we will quickly check this. So the equality of elements in a set is expressed by the diagonal relation. You may recall that from our video on relations. The diagonal relation is defined as the subset of the Cartesian product of X, which contains all the pairs XX, so where both entries are identical. And this is an equivalence relation. We will quickly check the 3 properties, even though they're quite obvious. It is reflexive, since X equal to X for all elements in our set is true by definition, so every element is identical to itself. It is symmetric because saying that X equals Y is the same as saying that Y equals X. And it's transitive because if x equals y and y equals z, then obviously x equals z too. So it's very easy to see that equality is an equivalence relation. And one way to think about equivalence relation is that they can filter out irrelevant information if we are working with a set that in a way contains too much information for our purposes. So the following example should illustrate that. Let the set S be the set of students at a school. And well, if you have students in a school, then you need to schedule lessons and assign teachers. So for each student, we need to assign teachers and lessons, but it's too inefficient to do this for every individual student. So what we do is we divide students into classes. Let's call them C1 to CK. And then these tasks of assigning teachers and scheduling lessons are performed for each class. So on a per class basis and not for each individual student. So in our set of students, the only relevant attribute for each individual student is which class the student belongs to. And of course, students have many other attributes that distinguish them from one another, such as name, age, height, or their grades. But these are completely irrelevant when it comes to these tasks of assigning teachers or scheduling lessons. So what all that matters is which class they're in. And for the purpose of these tasks, assigning teachers and scheduling lessons, we can consider all students, as 1 is 2, say, that are in the same class as identical. We may identify them with their class under this point of view. And dividing students into such classes creates an equivalence relation on the set S of students, where we say that student 1 is equivalent to student 2 if they are both in the same class. Now every student is part of a unique class in this school, so that the set of students is the union of all the classes. And also because no student is part of 2 classes at the same time, the intersection of the different classes are empty. So in other words, S, the set of students, is a disjoint union of the classes. Now this example may be a bit unexpected when you see it for the first time, but it is one of the most fundamental equivalence relations of all. So this is the so-called congruence relation modulo some integer n. Now, in the set of integers, we fix some number n greater or equal to 1, and we ask which remainder a given number x from the integers has when we divide it by this fixed number n. Now, if we divide by n, the possible remainders are the numbers 0, 1, up to n minus 1. So everything that fits between 0 and n. And let's say our number x has remainder k, which is one of these numbers from 0 to n minus 1. Then this means x has the following form. X equals k plus some multiple of n. So there's some integer a, and we take a times n. So we have a multiple of n here plus k. And when we divide x by n, do an integer division, then this is the multiple of n that we get from the division, and the remainder would be this number k. And in this case, we say that x is congruent k modulo n. Bit of an old-fashioned terminology, but that's what we call it. And the notation we use to express this is x with this sign, x congruent k mod n. Now, for our given n, this relation here is in fact an equivalence relation on Z. If we extend it to all the elements of Z, so we say x and y are equivalent if both x is congruent to k mod n and also y is congruent to k mod n. So in other words, x and y are equivalent if they have the same remainder on division by n. And so we can extend this notation here, or this notation rather, to express this equivalence relation, and we write x congruent y mod n for arbitrary integers x and y if both of them have the same remainder on division by n. Now we will prove that this congruence modulo n is indeed an equivalence relation. First of all, that it's reflexive is clear because, well, every element x has the same remainder modulo n as itself. So that's really a no-brainer here. It is symmetric. This is also clear because two things being equal is a symmetric property. So if two numbers x and y have identical remainders modulo n, then that is symmetric. It's also transitive, and we will look at this in a bit more detail. So if x is congruent to y mod n, this means, if we write it out, that there exists ab in the integers and some number k between 0 and n-1 such that x equals k plus a times n, so k plus some multiple of n, and y equals k plus some other multiple of n. Okay, so they have the same remainder k on division by n. And now if also y congruent to z mod n holds, then this means there exists some other integer c such that z equals k plus cn, because y has remainder k, and if it's congruent to z, then z must have the same remainder on division by n. But k was also the remainder of x modulo n, so altogether this means that x is congruent to z modulo n if we assume that x is congruent to y and y is congruent to z modulo n, and this exactly means that the relation is transitive. Now, clearly every integer must be congruent to one of the numbers k between 0 and n-1, and we let k bar, so we write this remainder with a bar over it, denotes the set of all integers x that have the same remainder k modulo n. Okay, so k bar is the set which contains all the integers that on division by n leave the remainder k. For this we use the notation k plus n times z. So nz meaning all the multiples of n. Just take all the integers and multiply them by n, then you get all the multiples of n. And if you add k to this set, then yeah, you get all of these numbers here. And we call this set k bar the residue class of k. And what we see, because every remainder has to be a number in the set from 0 to n-1, that we can write the integers as a union of these residue classes. So it's a union of the residue class of 0, so all the elements which leave remainder 0, and all the elements which leave remainder 1, so the residue class of 1, up to n-1 bar, so the residue class of n-1 containing all the integers which have remainder n-1 on division by n. And note that in particular this first residue class here, 0 bar, is just nz, so it's the set of multiples of the integer n. Also, this is a disjoint union. So all of these different residue classes have empty intersection because, well, an element from the integers can't have two different remainders when we divide it by n. So if we have some different k and h from our set of possible remainders, then their residue classes are disjoint. For the case that n equals 2, this here is simply the fact that the integers are the disjoint union of the even numbers 2z, which would correspond to the residue class 0 bar, and the odd numbers 1 plus 2z, which would correspond to the residue class 1 bar. And for n equal 3, I have a little sketch here to illustrate it a bit differently. So the different colors correspond to the 3 different residue classes that we have. So when we have n equal to 3 and we do integer division by n, then we can get the remainders 0, 1, and 2. Now the class of 0 contains all the multiples of n. So the black numbers 0, 3, here we have minus 3, and then it would go on, if we continue the line here, it would go on with 6, 9, 12, and so on. And similar in the negative direction, minus 6, minus 9, and so on. Now, the number 1 has clearly remainder 1 when we divide by 3. Number 2 has remainder 2 when we divide by 3, and then we get to number 3, so we get to another multiple of 3, which again belongs to the same class as 0 because it has remainder 0 on division by 3. We get to the 4, which is 3 plus 1, so it has remainder 1, so it's in the same class as 1. And similar with the minus 2 here. Minus 2 is just minus 3 plus 1, so it's a multiple of 3 plus 1, so it's in the same class as 1. And similarly, 2 and 5 are in the same class because they have remainder 2 on division by 3. Now, this is an example in the plane, a geometric example, and it would be helpful if you've been exposed to vectors before and to vector arithmetic, but even if you haven't, then it should be possible for you to follow this example. And what I'm looking at here is a line L in the plane that goes through the coordinate origin here, where the axes meet. And the direction vector of this line is the vector 2, 1. So I can write this line in set notation as follows. L is the set containing all the vectors t times 2, 1, where the parameter t runs through all the real numbers. Let's look at it in this sketch here. So the vector 2, 1 means we go 2 steps along this axis and 1 step along this axis. Then we have this vector. And if we multiply this vector by some number t, that means we either stretch or shrink this vector, depending on whether the number is the absolute value of this number is greater or less than 1. And so all the stretched or shrunk versions of this vector lie on this line. So if we take the set where this parameter t runs through all the real numbers, then it precisely traces out this line through this vector 2, 1 here. So you should think of this as extended to infinity in all directions. Now, we define an equivalence relation on the plane R2 with the help of this line. Namely, we say that two vectors, x and y, should be equivalent if x and y lie on the same parallel line to L. Okay, note that here the letters x and y mean vectors in the plane. They do not mean individual coordinates. what does it look like? We can see this in this little sketch here. X and Y lie on this red line. So the red line is parallel to our original blue line L, so they are equivalent. And this equivalence relation is the same as saying that Y lies on the line X plus L. So X plus L is by definition this set here. We take the vector X and add to it some vector V from the line L. For example, this blue vector here. We add it to X, then it points precisely to our vector Y, for example. And if we run this through all the vectors V that lie on this blue line here, then it traces out the red line. Okay, so we just push the blue line upwards by this vector X. And this is the same as saying that the difference vector from Y to X is contained in L. Let's look at this here. So the difference between X and Y is just actually the negative of this blue vector here. So that would be the vector going from the origin down here, and that's contained on the line L. And it's also the same as saying that X plus L is the set Y plus L. Okay, so instead of X plus L, I could also write Y plus L. Because if X and Y differ only by an element from the blue line L, then in this set here, at some point I can take this element X minus Y in L, add it to X, and then I'm left with, well, minus Y actually, but I could use the negative vector, which is also on L, and then I get the element Y in here plus running through all the vectors of L. Now, this is an equivalence relation because clearly it's reflexive, because X lies on the same parallel line as itself. There's nothing to show. It's symmetric because by what I just explained, X being equivalent to Y means that X plus L equals Y plus L. And again, because we can just turn around this equality here, so this also means Y is equivalent to X. And hence it's symmetric. It is transitive because, well, suppose that X is related to Y and Y is related to Z. This means that Y lies on the line X plus L and Z lies on the line Y plus L. But now we know that here Y plus L is the same as X plus L because X and Y are related. So Z is in the line X plus L, and this means X is related to Z, and hence transitivity holds. And we make an important geometrical observation here. We can completely decompose the plane R2 into parallel lines of L. So here I indicated that with a few of the parallel lines which have integer multiples of X as their difference, but of course between these sample lines there are infinitely many other parallel lines that make up the whole plane. So yeah, we can say we slice up the plane into these disjoint parallel lines, and for every vector X that is not on the line L itself, we can write any line in this decomposition as L plus T times X for some real multiple of X. So think of this vector X, and if we take all the multiples of X, T times X, running T through all the real numbers, then we are running through all the vectors here on this transversal line to L. And if we add L to each one of these vectors, we get a distinct parallel line for each different value t. So again, we have our set on which we have the equivalence relation is decomposed as a disjoint union of these sets of equivalent elements. And that brings us to part 2, partitions. So there's one common thing to observe in the previous examples. The set X, on which the equivalence relation was defined, is decomposed into a union of disjoint subsets. X equal C1 union and so on, union CK. So whatever these subsets were could differ from example to example. So in the one example, these subsets here were the classes in a school. In the next example, they were the residue classes. And in the last example, they were parallel lines in the plane. And as we will see, this is in fact characteristic for an equivalence relation. And we make the following definition for this. X is a set, and then we have a set of subsets, which we denote by this curly C. And we call this collection of subsets a partition of X if it satisfies the following two properties. Every element in our original set X is contained in one of the elements of the collection of subsets C. So this means X equals the union over all the sets C, so this is a subset of X, contained in this collection curly C. And the second condition is the elements of the collection C are disjoint. So if I pick any two subsets C prime of X that are contained in the collection curly C, then their intersection is empty. And maybe you recall that these were the properties we had for our unions of disjoint subsets in the previous examples as well. But in the general definition, we do not assume that the collection C is finite or countable. So it doesn't always have to be finitely many elements, as in the example here. Now, if X is a set and it has an equivalence relation tilde on it, then for any element X in our set big X, we can consider the set of all elements Y in X that are equivalent to element X, and we write this set in the following notation: bracket X and closed bracket. And this we call the equivalence class of X with respect to this equivalence relation tilde. Usually it's clear from the context which one that is, so we don't always state it explicitly. And sometimes we also write X bar instead of bracket X because it's a bit easier to write many times. So for example, we did that before in the congruence relation. And note that what this means is if X and Y are equivalent to each other, then the equivalence class of X is the same as the equivalence class of Y. And we can call any element Y in the equivalence class of X, which is the same as the equivalence class of Y. Any such element we can call a representative of that class. So an element from this set here represents the whole class of equivalent elements. And now an equivalence relation actually gives us a partition on the set X. So X is given with an equivalence relation on it. And then we have the following system of subsets. C, curly C, is the set which contains all the equivalence classes for the elements in our set big X. And then I say this set curly C is a partition of X. So recall what that means. It means that X is the union of all the equivalence classes. So if I take all the equivalence classes for the elements of x and take the union over them, then I get my full set x, big X back. And for x and y, two elements from our set big X, either we have that their equivalence classes are identical, or the intersection between the equivalence classes is empty. So this just means that the collection of equivalence classes is a partition. Now, the partition we obtain from an equivalence relation is usually denoted by this notation. So rather than curly C or something, we usually write x slash tilde, so the symbol for the equivalence relation. And we read this as either x over tilde or x over the relation or x modulo the relation. Now we want to prove this theorem. So any element from the set X is contained in one of the equivalence classes, namely the one defined by itself. X is contained in bracket X by reflexivity. So the equivalence relation requires that X is related to itself, so X is contained in its own equivalence class. And from this it is clear that X, the set big X, is the union of all the equivalence classes, because every element of X appears in one of these equivalence classes here. And if we take the union, then we have all the elements of X back together. So that proves the first part. For the second part, now we have to show that if X and Y are elements of X, then one of these two cases is true. So we might just assume that the intersection is not empty because, well, if it's empty, then it's this case, and we just have to show that in the other case, they must already be identical, the two equivalence classes. So let us assume that the intersection of bracket X and bracket Y is not empty, which means there exists some element Z in the intersection of bracket X and bracket Y. And by definition, this just means Z is equivalent to X and Z is equivalent to Y. So Z being an element here is this, and Z being an element here is this. Now, any element X prime in bracket X is equivalent to X. So this means Z is equivalent to X prime by transitivity, because Z is equivalent to X, X prime is equivalent to X, and hence Z is equivalent to X prime. That's just what transitivity means. And again, by transitivity, X prime is also equivalent to Y. So because X prime is equivalent to Z and Z is equivalent to Y, then this means X prime is equivalent to Y. So X prime is contained in the equivalence class of Y, and this proves that the equivalence class of X is contained in the equivalence class of Y. But now we can just reverse the roles of X and Y. So we, instead of X prime, we take a Y prime in bracket Y, and then we find in exactly the same way that Y bracket is contained in X bracket. And this means the equivalence classes are identical. And this proves the second part. And so we have shown that the collection of equivalence classes is a partition of the original set X. And we can also formulate a converse to the previous theorem, namely that every partition on a set gives rise to an equivalence relation. So this basically means that partitions and equivalence relations are effectively the same thing. This is theorem 9. So we have a set X and we let curly C be a partition of the set X. And now we can define an equivalence relation such that curly C is precisely the set of equivalence classes. And we define this relation in the following way. X is related to Y if X and Y are contained in the same element of curly C. Then this is indeed an equivalence relation, and the equivalence classes for this relation are precisely the elements of the partition C. So first we show that this indeed defines an equivalence relation. And here reflexivity and symmetry follow straight from the definition. So x and y being contained in the same element is the same as saying y and x are contained in the same element. And of course, a single element x is contained in the same element of C as itself. So there's nothing to show for those two. For transitivity, assume that x and y are related in this way. So this means there is some subset of x, C, which is contained in the partition curly C, and x and y are both contained in this subset C. Now if also y is related to z, then this means that there's some subset C prime in the partition C, such that y and z are contained in C prime. So this means y is contained both in C and C prime, so it's in the intersection of the two. And this means the intersection of C and C prime is not empty. But because curly C is a partition, we only have the case that either the intersection of two elements from the partition is empty, or if not, then it follows that C and C prime must be the same set. So this intersection contains y, so it's not empty, and this means C must already be all of C prime. And yeah, what this means is that x is related to z. So z being in C prime is also an element of C, so x is in C, and this means x is related to z. And we've shown transitivity, and this means our relation defined here is indeed an equivalence relation. And next we show that the sets that make up the partition are the equivalence classes. So suppose C is some element of this partition, some subset of x contained in curly C. If x is an element in C, then C is contained in the equivalence class of x by the definition of our relation. Now, why is that? Because the elements of C are all contained in the same element as the one where x is contained, and that means they're all related to x. So they're all contained in the equivalence class of x. But on the other hand, if we pick any element from the equivalence class of x, this means by definition that y and x are equivalent, and again by definition of this relation it means that y is contained in the same element of the partition as x is, which is C, so y is an element of C, and this means that also the equivalence class of x is contained in C, and this means C is identical to the equivalence class of x. And in this way we have shown that each element of the partition is an equivalence class. If we want to visualize an equivalence relation, we can do this with graphs. And the graphs for equivalence relations have very particular forms. So first of all, the graph is undirected because the relation is symmetric. Then every vertex in the graph has a loop because it's reflexive. So you see that in these little loops at every vertex here. Every equivalence class corresponds to a connected component of the graph. So here we have 4 different equivalence classes. And in every connected component, each vertex is connected to every other vertex by an edge, which is a consequence of the transitivity. well, you can see this in this component C1, the red one, and yeah, in the others of course too. Now we've seen that partitions and equivalence relation correspond to one another, and this means we can make the following definition. So given an equivalence relation on a set, on the set X, as usual, we call the partition X over the relation. Recall this notation here. We use this for the partition induced by the equivalence relation. We call this partition the quotient set of X under the relation tilde. And it's a bit of a mysterious name maybe why we call this the quotient set. And this name will make more sense once we take a course on algebraic structure, so that's not what we will do here, but we leave this to another course that will hopefully appear soon on my channel. And let me just observe, to make a bit more sense of this terminology, that if we have a finite set X and in addition all the equivalence classes of this relation have the same cardinality, then indeed we have that the cardinality of this quotient set is the quotient of the cardinality of X by the cardinality of any of its equivalence classes. We return to the modular relation to illustrate what a powerful concept equivalence relations and their quotient sets are. And I want to begin with some hand-waving to motivate the constructions using quotient sets, as this appears to be a reliable source of confusion for beginners in mathematics. So follow closely and rewind the video if you missed anything. Recall that we described equivalence relations as generalized equalities. So when dealing with an equivalence relation tilde on a set X, we are only interested how the elements differ with regard to this equivalence relation and not with regard to any properties that are not encoded in the relation. For example, we only care which class the student is in, but we do not care about the student's name or age. We only care what the remainder modulo n of a number x is, but not what multiple of n this number contains. Or we might only care about which parallel line a given point lies on, parallel to some given line L, but we don't care where particular this point lies on the line. So if we do not care about which element within an equivalence class we consider, we might as well work with the equivalence class itself, rather than working with the individual elements in that class. And this means that we are really interested in the elements of the quotient set X over tilde rather than the elements of the original set X. So instead of considering the equivalence classes as subsets of X which contain equivalent elements, we move over to considering the equivalence classes themselves as elements. And the right set to do that in is this quotient set. This idea is of paramount importance in modern algebra, where it provides a standard method for constructing new algebraic structures. And next, I want to illustrate this by constructing so-called modular arithmetic using the congruence relation, so the modulo n relation that we got to know in example 4. Recall that the congruence relation, modulo n, views two integers as equivalent if they have the same remainder on division by n. And this might seem a bit exotic when you see it for the first time, but we actually use such relations much more often than we might think. For example, we use it in computers. If a computer has n-bit arithmetic, so at the current time n equal to 64 would be reasonable, then in this computer we can represent only numbers up to 2 to the power of 64 minus 1, at least if we hold the numbers in the registers or the processor of the computer. So if a number grows beyond that bound, then a so-called overflow happens, which means it reverts back to a smaller number, namely its remainder modulo 2 to the power of 64. Or a simpler example is the phase of a clock, which shows the numbers from 1 to 12. And if one of the digits runs past 12, then it starts back at 1. So when adding hours to the current time, multiples of 12 don't matter, because the clock has no way of displaying them. We can only care about the remainder modulo 12, because that's all the clock can display. So I illustrate this here. We have a clock which at this moment displays 9 o'clock. And if we add 5 hours to 9 o'clock, then, well, 5 plus 9 is 14, but our clock runs past 12, so it points to 2 o'clock. And 2 is exactly the remainder of 14 modulo 12. So the clock doesn't know that we had already 9 o'clock before, it just displays 2 o'clock. And even if we add multiples of 12 to our 9 o'clock, then the clock, of course, still won't take that into account when displaying the new time. So here I add 34 hours to 9 o'clock. So I go around once with 12 hours. I go around twice with another 12 hours, so that makes 24 hours. And I'm back at 9 o'clock. And then I have 10 hours left from my plus 34. So I go past 12 again for 10 hours and arrive at 7 o'clock. And that is because, well, 34 plus 9 is 43. And that 43 has remainder 7 modulo 12. And what we really do here is, when we compute modulo n, we introduce a new law into our integer arithmetic. So this new law is n equal to 0. And of course this is not true in the integers if n is anything other than 0 already. But when we compute times on the clock, this becomes true. So there's a different arithmetic here than the usual integer arithmetic, even though it looks very similar. And with this new law, any number in the integers will become equal to its remainder r after introducing the new law, modulo n, of course. This is because x is equal to r plus a times n, where r is the number between 0 and n minus 1. And here we have some multiple of n. But if the new law applies with n equal to 0, then this becomes just 0. So we have x equal to r plus 0. So x and its remainder modulo n are the same after applying the new law. And on the clock, for example, where we have n equal to 12, the new law would be 12 equal to 0. And the result of that is that all the integers that differ only by a multiple of 12 would become identical after introducing this new law. For example, look at these. 15 is equal to 3 plus 1 times 12. 27 is equal to 3 plus 2 times 12. Minus 141 is equal to 3 plus minus 12 times 12. And 3 is equal to 3 plus 0 times 12. Now if we introduce the new law 12 equal to 0, then this and this and this and this would all be 0. And all these would become identical. Of course, taken as integers, these numbers are all distinct. But the residue classes modulo 12 are identical. because we see they all these numbers here have remainder 3 on division by 12. So the class of 15, the class of 27, the class of minus 141, and the class of 3 are all identical modulo 12. And so it makes sense to take these residue classes as the elements for this new arithmetic where n equal to 0 or 12 equal to 0 in this case holds. So the proper set on which we realize this new law n equal to 0 is actually the quotient set. So the set containing all the equivalence classes, z over the congruence. And just for the notation, it's not customary to actually write it like this, but usually you would use one of these two notations, so either z over nz or simply zn with n as an index for this quotient set modulo n. And I would say this is probably more popular with mathematicians, and the second one is more popular with computer scientists. And now I want to make all of these ideas precise, but before that I will prove some interesting properties for the congruence relation mod n that are quite helpful when dealing with them. So first we have this little lemma here where we have an equivalent description of the congruence relation. Now n, let it be greater or equal to 1, and we have two integers x and y. And then x minus y is contained in nz, so x minus y is a multiple of n, if and only if x is congruent to y modulo n. Okay, so we have an equivalence that we need to prove, so we need to prove two directions. First, we prove that when we assume that this is true, then the right-hand side holds, and in the next step we assume that this is true, and we will show that the left-hand side follows. Okay, but first we do this direction, so now we assume x minus y is a multiple of n. And suppose that x has remainder k on division by n, so x is congruent to k modulo n for a certain number k between 0 and n minus 1. This means we can write x in the following form. X is k plus an, so k plus some multiple of n. Now the assumption we make for this direction is that x minus y is a multiple of n, so we can write x minus y equal to bn for some number b. And now we can first solve this for y, so we have y equal to x minus bn, and then we plug in this expression here for x, so we replace x by k plus an, but then we have k plus a minus b times n. So y equals k plus a multiple of n, and if we divide by n, we get the remainder k for y as well. This means y is congruent to k mod n, and if y is congruent to k mod n and x is congruent to k mod n, then we have shown the right hand side, then x is congruent to y mod n. Now we do the other direction. We assume now that x is congruent to y mod n, and we want to prove that their difference is a multiple of n. So x congruent y mod n means that a is of the form k plus an and y is of the form k plus bn, so both have the same remainder k on division by n, and to that added some multiple of n. Then we look at their difference. X minus y is k plus an minus k plus bn, so we just plug in these expressions here for x and y. And well, these two k's here, they just cancel out because this one has a negative sign. So what we're left with is a minus b times n, and that is a multiple of n. So we've proven the other direction as well, and we have thereby shown this equivalence here. Now, a congruence relation is a very special equivalence relation in a sense that it is compatible with the arithmetic of the integer numbers in the following sense. Again, let n be greater or equal to 1, and we have 4 integers x, y, kh. We suppose x is congruent to k mod n and y is congruent to h mod n. And then if we take the sum of x plus y, this is congruent to k plus h mod n. And if we take the product x times y, this is congruent to k times h mod n. And we want to prove this. So by assumption, x equals k plus an and y equals h plus bn for some ab, because they're congruent, so their difference is a multiple of n, as we have just seen in the previous lemma. Now we compute x plus y, and we replace x by this and y by this. So x plus y is k plus an, and y is h plus bn. And if we rearrange the items here, we get k plus h plus a plus b times n. So k plus h plus a multiple of n. So x plus y is in fact congruent to k plus h mod n, because x plus y and k plus h only differ by a multiple of n, so they are congruent mod n. And similar for the product, x times y, again we plug in k plus an and h plus bn for x and y, and then we just compute. We get k times h plus kbn plus han plus abn squared, and this is k times h plus something times n. So we have k times h plus a multiple of n, and this is congruent to k times h mod n. So overall, x times y and k times h are congruent modulo n. And with the help of this proposition, we can define clock arithmetic properly. So we can declare an addition and a multiplication on the quotient set z over nz. And we do it in the rather obvious way. So for a given n, we define an addition plus and a multiplication by a dot on z over nz as follows. So here the bars indicate the equivalence classes, or the residue classes in z over nz. The class of x plus the class of y is by definition the class of x plus y. And the class of x times the class of y is by definition the class of x times y, where we take x and y to be two integers, and with the bars we indicate their residue classes, as I said. Now, be careful which plus and which dot we refer to here. Here we have the addition in the integers, and here we have the multiplication in the integers. And then after we add x plus y, we take the equivalence class. And this equivalence class we define to be the sum of the equivalence class of x and the equivalence class of y. And similarly for the multiplication here. So these are the newly introduced addition and multiplication on the quotient set. And here we use the usual multiplication on the integers and then go over to the quotient set after adding or multiplying. And so we define the addition and multiplication on the quotient set by referring back to the integer multiplication and addition and then taking the residue classes. Now there's one important thing to note here. We use specific representatives of the residue classes. So in order to define the addition and multiplication on the classes, we refer to particular elements x, y, and z, because on the right hand side we use these representatives for the addition in the integers. And whenever we make a definition like that on some quotient set by using the representatives of the equivalence classes, we have to make sure that these operations are well defined. So I gave this the name 1, so we have to make sure that addition and multiplication in equation 1 are well defined, which means they are independent of which representatives I could choose to define it. And this is something we need to check. And in fact, we've essentially done this in proposition 12, because if we choose any representatives k from the class of x and h from the class of y, then proposition 12 tells us that k, class of k plus class of h, equals class of k plus h. That's just by definition. And by proposition 12, we have that k plus h is congruent to x plus y modulo n, because k is from the class of x and h is from the class of y. So this then by definition is x class plus y class. And so if we choose different representatives of the classes x bar and y bar, we get the same result. And the same holds for the multiplication. Again, because of proposition 12. So here, this equality holds by definition. If we multiply the two classes, then by definition here, this is we multiply the representatives and then take the class of that. And again, by proposition 12, that is the same as if we do the thing with x and y, because k is congruent to x and h is congruent to y. And so this shows that the operations defined in 1 are indeed well defined. That means they are true regardless of which representatives they are consistent irrespective of which representatives of the classes x bar and y bar we choose. Now, an exercise for you. Pause the video and compute in z over 12z the following things. Add 4 plus 23, or rather the equivalence class of 4 and the equivalence class of 23, modulo 12. Multiply minus 12 times this large number, or rather the class of this large number. Find a positive integer x such that x bar plus 10 bar equals 0 bar. And find some integer y such that bar y times bar 7 equals bar 1. This may take a bit longer, so be sure to rewind the video to clarify things if necessary. And here are the solutions. So 4 plus 23 modulo 12. Well, we have 23 being 24 minus 1, which by definition of the arithmetic in z over 12z is 24 bar minus 1 bar. But 24 is a multiple of 12, so this is actually 0. So we have minus 1 in 12 over 12z. And if we add 4 to 23, then this is actually 4 plus minus 1, so 4 minus 1, and this makes 3. For the second one, well, we have minus 12 being a multiple of 12, so this is actually 0 in 12 over 12z. So this whole product here is actually 0 times whatever that number is, so it's 0. For number 3, we can take x equal to 2, and then we have the residue class of x plus the residue class of 10, so that's 2 plus 10 residue class, and that's 12. But modulo 12, this is 0, so this is x equal to 2 is a solution to this question here. But in fact, there are many solutions, infinitely many even, because any x of the form 2 plus 12a with a greater or equal 0a would have done here. Now, for the fourth one, finding y such that y times 7 equals 1 modulo 12. This means we need to find some integer y such that y times 7 is 1 plus 12a for some integer a. So 1 plus a multiple of 12. And for example, y equal to 7 satisfies this because modulo 12, y times 7 is 7 times 7, 49. 49 is 1 plus 48, 48 being a multiple of 12. So this is 0 modulo 12, and we are left with 1. So that's an interesting thing because modulo 12, we have that 7 times 7 equals 1. So 7 is its own inverse, modulo 12. To recapitulate what we have learned now is we have seen by the example of modular arithmetic how we can use quotient sets to construct new algebraic structures, in this case z over nz, out of a given algebraic structure, in this case the integers with their usual arithmetic. And we have interpreted this as taking the given algebraic structure and introducing new laws into it. In this case only the law n equal to 0 if we compute modulo n. And now all the expressions in the given algebraic structure, so in z, in the integers in our case, all those expressions become identical under this new law that are combined into an equivalence class. And then going over to the quotient set as the new algebraic structure, we have a set or an algebra in which this new law holds. It inherits the arithmetic from the given algebraic structure, but then in addition has this new law on it. And this is something that I will explore in much more depth in a course on algebra that I hope to eventually publish on this channel. So watch this space. And that concludes our study of modular arithmetic. And we now look a bit more closely on how quotient sets and maps can be compatible. And we will do this now, exploring how equivalence relations can be compatible with maps between sets. In this section, I will always write x bar for the quotient set. So I won't use this notation because it's a bit too cumbersome and x bar is just easier to read. So the first thing I'll do is I'll formalize the notion of replacing an element x by its equivalence class x bar in the quotient set. And this is just done by a very simple map. If x is our set and tilde an equivalence relation on x, then the map P from x to x bar, which simply maps each element x to its equivalence class, is called the canonical map, or often also the canonical projection for the given relation tilde. And I illustrate this in this little image here on the side. So here's x with its elements, and the different colors indicate the equivalence classes of tilde. And so each equivalence class has a few elements of x in it. And the projection, the canonical projection, maps these to distinct elements in the quotient set. Okay, so each of these classes here becomes an element, a single element down here. And if we go back to the congruence relation once more, then the canonical map for the congruence relation modulo n is, well, the map P from the integers to z over nz, which maps x to its residue class. So the residue class, of course, being the class for the remainder of x on division by n. And we've seen in proposition 12 that this canonical map has the following property. If we apply the canonical map P to the sum of x and y, then we get the sum of the residue classes of x and the residue class of y. Now here, this is the plus in the integers, and this is the plus in the quotient set in z over nz. And similar for the multiplication, if we apply the canonical map to x times y in the integers, then the result is p of x times p of y, but now the multiplication is taken in the quotient set z over nz. And later in a course on algebra, we will get to know this property here as the homomorphism property. So a map P with this property is called a homomorphism, and that means it's a map that preserves the algebraic structure of the integers on z over nz. So when projecting from the integers to the quotient set, we can just use arithmetic, use addition and multiplication in a straightforward way. And now I want to say what I mean when a map between sets is compatible with an equivalence relation. This is the following proposition. So we're given a set X with an equivalence relation tilde, and here we have the canonical map P from X to the quotient set. And suppose there's some map F from X to Y, where Y is some other set. And then the following two statements are equivalent. There exists a unique map F bar from the quotient set X bar to Y with the property that F bar composed with a canonical map is the original map F. And this statement is equivalent to saying that the map F, the original map F, is constant on every equivalence class of tilde. So that means for every two elements from the set X that are equivalent under this relation, the map F assumes the same value. It maps them to the same element in Y. Now the map F bar from X bar to Y is called the quotient map induced by F. So reasonable naming because it goes from the quotient set to Y, and it is of course induced by F because its values are determined by the original map F. And yeah, so what this means is that if the second condition of this proposition holds, then the map F can be transferred to this map on the quotient set. And before I prove this theorem, let us better understand what the statement is. So here we have a set X again and the quotient set X bar for the equivalence relation with the canonical map. We are given this map F into some set Y, and now the question is, do we have this F bar such that mapping an element from X to Y is the same as first mapping the element to the quotient set and then mapping it from the quotient set to Y using F bar. So this is this property that says in this diagram, it doesn't matter whether you go this way or whether you just go straight with the map F. Now to illustrate what should happen here, if F is constant on each equivalence class, that means that all the elements in one equivalence class are mapped to the same element in Y. Now the canonical map maps all of these to one element in X bar, and because they're all mapped to the same element here, we can now prescribe that F bar should map the equivalence class to this particular element that all the elements of the class are mapped to. And this has to be true for all the equivalence classes in X. So if this class gets mapped to a different element, then we can just take the class in the quotient set and map it to that one, and similar for this and for that one. Now, in what situation would this actually go wrong? When can we not find such a map F bar? let's illustrate it here. So we have the equivalence class, the red class, which is mapped to z bar in the quotient set. But the elements in this class are actually mapped to different elements in y. So these two here are mapped to this one by f. But this one is mapped to a different one here. And the one up here is yet mapped to another one here. So if we were to define this map f bar, which just assigns one image for the full equivalence class, then which one should we pick? There is no unique candidate. So we can't just assign 3 different values for a function, because then it's not a function. So yeah, we would have to pick one, but then it would not have the property required from the proposition. So in this case, such an f bar would not exist. Okay, now I hope it's a bit clearer what this proposition states, and let's get to the proof. So here's our proposition again, and as I said before, we need to prove that this statement implies that one, and also that this statement implies that one. First, we assume the first statement as given, and we want to show that the second statement holds. So we need to prove that if we have such a map f bar with this property, then f is in fact constant on every equivalence class of tilde. Now, for that we take 2 elements, x and x prime, from our set big X, and we assume they are equivalent. What we need to show is that they have the same value under the map f. Those two being equivalent means that the projection, the canonical projection of x, equals the canonical projection of x prime. So this is their equivalence class x bar in the quotient set. And now we apply this. So we look at f of x, which by assumption equals f bar composed with p applied to x. So this is true by assumption, because we assume part 1 to be true. Now this means nothing but f bar applied to p of x, but we assumed they are equivalent, so p of x is equal to p of x prime, so we can replace that here. So this is f bar applied to p of x prime, which again is just f bar composed with p applied to x prime. And again, we assume that this holds, so this is just f of x prime. And so we see that f of x prime equals f of x, and so we see that f is indeed constant on the equivalence class of x. And x was an arbitrary element, so we can pick one such element for each equivalence class, so f is constant on all the equivalence classes, on each individual equivalence class of this equivalence relation. Now we do the opposite direction. We assume now that statement 2 is true, and we want to conclude the existence of such a map f bar. We define it in the obvious way. We define f bar on x bar to be simply f of x for all x in our original set x, big X. And the assumption is that f is constant on the equivalence class. So this will give us that this definition is well defined, because here we define the map f bar on a class by using a representative of the class, and we know that because f of x and is equal to f of x prime for all equivalent elements x and x prime, that this definition is independent of which representative of this class we choose here. And this means that f bar from x bar to y is a well-defined map. And now we need to show that it indeed has this property here. Now x bar is nothing else but p of x, so the canonical map applied to x. And since we defined it in this way, it immediately follows that f is equal to f bar composed with p. And it is indeed a unique map, since this is the only way to define such a map f bar which satisfies f equal to f bar composed with p. And now we're done. This is the proof of proposition 15 and the equivalence of these two statements. So maps that are constant on equivalence classes induce such maps on the quotient sets. And now I want to prove something about the so-called canonical factorization of maps. And for this, you should recall the notions of injective, surjective, and bijective maps from chapter 3 of this course, in case you have forgotten them. So if you don't recall what this means, please go back to the video for chapter 3 and watch that part about injective, surjective, and bijective. And the canonical factorization theorem is now that if f from x to y is a map between these two sets, then we can define an equivalence relation on x by x being equivalent to x prime if they are mapped to the same element under f. So if f of x equals f of x prime. Okay, now note here we just begin with a map. We don't start with an equivalence relation, but when we're given this map, we then define an equivalence relation on x by this rule here. And then we have that f is equal to I composed with f bar composed with p, where I is the inclusion map. So I maps f of x into y, and this is an injective map. F bar is bijective. It's the induced quotient map on the quotient set x bar for this newly defined equivalence relation, mapping it to the image of x under f, which is a subset of y. And p from x to its quotient set is surjective, and this is just the canonical map. So it's indicated in this little diagram here. We are given f from x to y, then with this newly defined equivalence relations, we have the canonical map to the quotient set for this relation. We have the induced map f bar going to the image of f. And then, because this is a subset of y, we can apply the inclusion map to it and include it into the set y. And now taking an element x and applying f to it is, the theorem claims, is the same as going this way. So at first applying the canonical map, then the induced map, and then the inclusion map. And what this means is that any map f between two sets can be decomposed into a sequence of a surjective map, a bijective map, and an injective map. And we want to prove this, so just for space reasons, I just put this diagram here as a reminder what the statement of the theorem is. So given this, we have this composition here. Now, from the definitions, it is clear that the inclusion map is injective, so that's not something we need to prove because it just maps every element to itself, only that we now assume it's in a possibly bigger set. And it's also clear that the canonical map P is surjective because every equivalence class has some element from the original set X that gets mapped to it. So this is clearly surjective. Now the relation tilde that we just defined, where we said two elements of X here are equivalent if they are mapped to the same element in Y. This is an equivalence relation, and it follows directly from the equality relation between the images here. So there's nothing to prove. Now, by design of this equivalence relation that we introduced, f is constant on the equivalence classes because we just defined our equivalence relation in that way. So by proposition 15, the map f bar here exists, and we have indeed that the composition of the inclusion map with f bar and p applied to an element x here equals I applied to f bar applied to p of x. This is just x bar by definition. Then this is just f of x because f bar is the canonical map. And the inclusion map applied to some element is just that element itself, f of x. So here we have shown that this composition equals f, because we can plug in any element x here, so they are identical on all the input values x. And this shows that truly the map f is the composition of these three maps. Now, the image of f bar applied to the quotient set is the image of f applied to x, and f is surjective onto its image, f of x. That's just by the definition of what the image is, and so it follows that f bar is surjective as well. Now what we want to have is that f bar here is bijective. So we've seen that it is surjective because f is surjective onto its image, f of x. And we need to see that f bar is also injective, so we can conclude that it's bijective, and that would conclude the proof of the theorem. Now, to show that it's injective, we pick two elements from x, such that the quotient sets of x1 and x2 are mapped to the same element under f bar. And what we want to show then is that the quotient sets of these two are the same, so that these two are equivalent. Now, by definition of the equivalence relations and of the canonical map, this means that f of x1 equals f of x2, just from the quotient map. And the way we defined our equivalence relation was that if they have the same images, if the two elements here have the same images under f, then they are equivalent. And this means that the equivalence class of x1 equals the equivalence class of x2. And it follows that f bar is injective because two equivalence classes having the same image under f bar implies them being identical. So f bar is injective, and together with the surjectivity that we already established here, it follows that f bar is bijective, and that concludes the proof of Theorem 16. And that concludes this chapter of the course. And for you, modulo liking this video and subscribing to my channel, there is zero to do. So please do that to support my content, and we will meet each other in the next video.